My name is Sinan Acikgoz and I'm an associate professor in engineering science. As you might have discovered if you've gone to see other talks, there's a very broad range of subjects that exist within this department. And my subject is construction materials and structural engineering. And I do a very small subset of that, although I'll try to talk a bit more generally about the sort of things that I do in research. And I will also talk about how that relates to what the current challenges we have, and also how that relates to the undergraduate degree here. So this doesn't seem to be working, so I'll just use that. Just a brief acknowledgement for all the students, collaborators, and funders, especially students. They're the main people who do the work. I'm in the lucky position to be able to talk about them. So many of you imagine structural engineering as the building of bridges, the building of tunnels, and iconic long span roofs, as this quote mentions, like the Wembley Stadium. And that's indeed an important part of what a structural engineer does. We design all of these structures, and they make the profession really visible. But at the same time, this has started changing in the past 10, 15 years. And this is a nice quote from the American Society of Civil Engineers, where it says, in the 1970s, structural engineers were among the first professionals to adopt computer analysis. Today, many design tasks that a structural engineer used to do are now being done by computers. And that certainly is true, that there's a lot of activities which are automatic now. Things we used to do by hand, you can do a lot of that by using computing. And also the final bit of the quote, which is what I find really interesting, which is also what I'll try to illustrate today, is that structural engineering, the meaning of what structural engineers do has now changed quite a lot. We work much more on the rehabilitation, reuse of what we have, the existing infrastructure, and we also work on making new infrastructure more sustainable. And these are the main axes of work. And they create other challenges that are less, what you might associate less with traditional structural engineering. But I hope I can convince you today that, the future of structural engineering and the future of most engineering is interdisciplinary, different, which requires different skills from different portions, different parts of engineering. So, structural engineers, we work with construction materials, and our task is, put very simply, to choose the most appropriate load-bearing material and optimize its use. What makes a material optimal? Many things. We can start with availability. Do you have it? We can talk about ease of construction. How easy is it to build? Can you carry it by hand? If you're doing something small by hand, that's very important. We can talk about strength, of course. We want our structures to be strong enough because we rely on them. We incredibly rely on our structures, and we hope that everything goes okay because we can live our life. If something goes wrong, it can go terribly wrong. So strength is obviously very important. Durability, structures last longer than us. So really long horizons for durability that we have to consider. Aesthetics, very important. These are places we live in, or work in, or commute in. Cost is something that's very important. We want it to be as cheap as possible. Sustainability is something that's being considered more nowadays. So here's a little chart, and this is a bit of a funny chart. So these are different columns that you can construct out of different materials, and you can imagine there's a load here. There's a 1,000 kilonewton compression load. How big does the material need to be, and how much carbon does it? What is the carbon footprint of that material? This reveals something quite interesting. The least carbon material, people would probably think about timber. Timber is known as a green material. And the most carbon emitting material, one would think, would be concrete, number 4. Well, concrete is indeed quite high in terms of the carbon scale. Steel is even higher. What really is surprising, though, is that the lowest carbon is from another material, which is stone, which is just a good old stone. So that is because a material like concrete will come from crushing of stone and being transformed into cement, and that is a whole industrial process, and there's burning inside that process, which releases a lot of carbon dioxide. Natural stone, you just need extraction. But of course, stone has got a lot of problems, but this is just illustrates to you how this set of materials that we have, we've got surprises when you start considering sustainability. And as it happens, this is not by choice, but stone is the material that I'm most interested in these, and that's what I'll be talking about today. Of course, there are complications. We cannot say it's the least carbon emitting material because that also depends on how far away you're from the quarry. But in terms of a material by material basis, stone is a good construction material, and that's pretty much the oldest construction material. What I'm interested in amongst all these materials is masonry. Masonry isn't a material, it's a craft of building a structure by individual blocks. You stack all them together, you bond them with mortar, and there you've got masonry. You can use steel in it, you can reinforce it with steel, then you'll have reinforced masonry. The numbers might sound surprising. Greater than 80% of the UK housing stock is masonry. So why? Because it's much easier to just build everything by brick. It's a bit like a building Lego. It's still very popular. People use it a lot. And our bridge stock, again, this is probably surprising, half of our bridge stock is masonry. They dates pretty much before the 20th century, but that's what we had built. So they pretty much date before the beginning of 19th century. But that's half of what we have today. So it's very, very significant. All this construction material, iconic buildings like Houses of Parliament would be constructed from masonry. But also, regular housing would be constructed from masonry. So there's an incredible range of things that you can construct with this this technique. And the reason that it interested me at the time when I started looking at this was it is taught very, very little in undergraduate courses. I'll talk more about that very briefly later on. What is the thing what are the materials that we use for masonry then? Well, a lot of different things. There's not one, a lot of them. We can think about blocks, like in this example from Keble College. You can have bits of stone here, bits of blue bricks, engineering bricks, bits of clay bricks. I don't know what these white bricks are, but there are different shades and types of materials that you can use for the blocks. In between the blocks, you've got bedding mortar. Mortar could be made from lime, it could be made from cement, it could be made from plaster. A lot of different materials again. You can have reinforcements. Reinforcement, if it's before 19th century, it could be wrought iron. If it's more modern, it could be stainless steel. And inside, when you go into these buildings, you'll often see beautiful plaster. Unfortunately, engineering department is the most beautiful one in this, so I cannot show you any nice ceilings here. Still plaster, but not as nice. But you can imagine in historic buildings, you can have really beautiful plaster ceilings. And this is an incredible range of materials, and which is what makes masonry quite interesting. There is a wide variety of materials, and the behavior of structures depend on those. And modern materials, for instance, in that house that I was just showing in the previous slide, would just be simple bricks that you can buy off, and they're not generally very well characterized for engineering purposes. So a lot of masonry is driven by expertise, by having constructed buildings, etc. So it's not. It doesn't always. It's a very challenging material to do engineering on because it's driven by expertise. So what is the toolkit of the structural engineer when we approach masonry? Well, we can do several things. I've simplified it here a little bit. If we want to understand materials, we can go into the laboratory. We can do laboratory testing. We could, for instance, take materials and we could look to crush them to understand their properties and to understand the mechanisms by which they get older. Because we're talking about materials which are used for hundreds of years sometimes, right? So we have to test how durable materials are under real conditions. It's not just good enough to test them under a loading condition. We also want to see under different humidity conditions, different temperatures that they will be subjected to. We can test materials. As well, we can test structural components, much bigger stuff, which is sometimes really interesting, and sometimes we do that. Sometimes the big stuff is difficult, so we'll use numerical modeling, computational modeling. So here I've got a wall, which is, you can see it's a computational model. It's got specific sizes, and we're looking at a specific test in there. We're simulating a specific test in there in the computer, which is called flat jack testing. But it allows computational models have improved so much in recent years that you can reliably predict response with them if you've got enough information. And sometimes computational models are helpful if you want to change your structure in some way. You've got a problem and you want to say, I want to change this. And I'll give you examples of this later on. There is also the field side of things, which is quite interesting. When you've got an actual structure, you want to monitor that actual structure to see how it's behaving, to control its response. And sometimes you want to detect and track damage. So if there is damage growth in structures, and there's always some in masonry materials, this technique is really useful to detect and track them. So just to give you some ideas, when do we need to know more about masonry materials? When do we need to use this toolkit? That's when these sort of things happen. We can have degradation. Materials might be getting older, or materials might be under the influence of things that are causing to degrade its performance. We might have hazards. They might be anthropogenic hazards, things that are caused by humans, or they could be natural hazards like earthquakes. You can also have environmental hazards, which I'll very briefly talk about. And part of the engineering toolkit is also to develop materials. We can develop materials or interventions to make our structures, to strengthen our structures against a given load. Or we also might wish to change our structural design system to develop more sustainable systems. So in all of these cases, we need to know more about masonry, and we need to put more science into it and use the bits of tools that we've got. Just to give you some examples of the strange structures that I deal with. So this is an example of a ceiling, which is from London, Institution of Civil Engineers building in Westminster. So the plaster ceiling is actually that. And just if you remove a bit of the plaster, what you see is bits of metal, bits of little gummy little suspending material like this that is holding up that ceiling. So you've probably never seen this, and it's for the better, because these materials are very, very fragile, and when they start failing, the whole ceiling comes down. So this is a material that's called fibrous plaster. It's composed of plaster done with jute fibers, and it's used in a lot of London theatres. A few years ago, you might remember there was a collapse in a London theatre. It's these things collapsing. It's these things starting to suck up water and then becoming softer. When they become softer, they become more porous. In that process, the internal little fibers inside this material, which are jute, start to be eaten away by fungus. So there's a whole process which degrades this material. And a few years ago, I met a plaster artist who was called on to replace some of these things. And she had a really big problem. How do I inspect these ceilings? Because it's very difficult to get to these things. We don't know where they are. We don't know where they're suspended, because when you look underneath, all you see is just plaster, decorative plaster. So this is the problem that one of my students investigated. And we used a technique called acoustic emission technology. What happens is when a material cracks, energy is released. Because the material around the crack it was stressed, and it releases the stress because there's now a crack. And though that instant release of stress creates waves inside the material. And these waves are in the ultrasound range, so kilohertz, very, very high frequencies. We've got microphones which can detect these. And if you look at this image, you can see some acoustic emission sensors which are all detecting a crack. And if you've got enough acoustic emission sensors, you can actually put them on your ceiling, and you can see where is this crack sound coming from. And by the way, this is an inaudible sound crack, so we cannot hear this. And these acoustic emission sensors cannot hear that I speak. So they work in a completely different range. You could have a concert in this place, and they wouldn't hear it because they're tuning on to much higher frequencies. So the interesting research problem here is acoustic emissions have existed for a long time, this equipment. The interesting research problem here that we had was this material is very heterogeneous. So the waves don't travel at regular speeds. So the wave speed changes inside the material. So the engineering side of things here was that we developed techniques which used artificial intelligence to actually understand where the failures are occurring. So now our idea was that you put these acoustic emission sensors underneath the structure, you don't open hatches, you leave them there for a while, you hear if there are any failures going on. And if there are any failures, you know where to focus and you know where to change. So this is a type of a problem that I wanted to give you an example of with regards to how you can use technology to deal with structures, historic structures such as this. Another one, closer this time to Oxford, Blenheim Palace has this problem. If you look at this photograph, you see a little bit of iron inside the masonry. That little bit of iron, when you expose it to water, parts of it will grow 10 times its original volume because of corrosion. And when that happens, it's got immense amount of power to crack through stone. So it's incredibly surprising when you see how powerful this can be. And when it can crack through stone, these bits of stone then fall on people, and they have to cordon off parts of the area. The problem is they don't know, why this is happening, and where they have their irons, because there's no record of that, right? So it's a difficult problem. And another practical problem they have is they want to replace all these areas which have blown off. They want to put some replaceable new materials. So one of my students is doing research on this, which is to understand what these materials are. What are the historic materials that we have over at Blenheim Palace? And can we find materials which are modern and resistant? And there are other parts of this project, but I won't talk about those. And I wanted to give this example because I just wanted to illustrate again how, structural engineering subject, and most engineering is like this. You get onto doing different things. It's not just mechanics, it's not just chemistry, it all gets together. It turns out that the Blenheim wrought irons, we've done quite a lot of characterization on this. It was done at a time when blast furnaces were found. So previously people used to have small little furnaces that they constructed on the ground. But blast furnace processes had started by then, but they have done this through, they have used charcoal fuel, which is only a period of 15-20 years that they did that. And it turns out that Blenheim irons had that property. And we saw that through chemical analysis because the phosphorus amount inside the metal was high. So interesting, it tells us what the material was. We can know that and we can use that information. We looked into limestones under a microscope. This is also under a microscope of the iron at the bottom. And we also looked at, we want to characterize these so we can choose materials that are compatible. And next thing we're doing is we're putting these materials, this looks like a bad photograph, but it's intentional. All these replacement materials for stones that we're looking at, we're testing them in corrosion chambers now. And the idea there is you subject materials to very harsh conditions within a short amount of time so you can replicate how the material would degrade over a very long period. So we can now use these tools to better understand degradation. So this corrosion chamber basically is a salt spray chamber. It changes, it can control temperature, it can control humidity, and it constantly sprays salt, which accelerates corrosion due to the presence of chloride ions. So this is another type of research that relates to masonry structures. Let's talk about hazards, maybe more traditional engineering that relates to construction. One of the hazards that we have is something that's quite necessary. To create transport, energy and waste underground infrastructure in urban areas, we need to use underground space. We need to dig tunnels. There is pretty much no space in most of our cities. And the tunnels underground are getting quite large. So you might have gone into Crossrail. You will have seen how large those cavernous spaces are now. And here's a photo, and you can see, this is from Bank Station. You can see how small the people are compared to the tunnel size. So these are 10-meter diameter tunnels. And they're happening beneath our feet, 20 meters, 30 meters, so not that far. And when they get constructed, the ground moves. That's just inevitable. And when the ground moves, you can have issues in the buildings above because they'll start to settle. And the sort of problems that we have to deal with here is how can we ensure we do not damage the existing buildings while we're delivering these essential services? Because the services need to be delivered, but we need to find a correct way to deliver them. And this needs to be done very early on in the project. We need to make sure we will not damage buildings. And the second question is, how can we quantify the impact of excavation on the buildings? Analysis might say something, but we really need to see what's happening in reality. So we need to do field monitoring. So these two questions are what I focused my research efforts on. And the tool that we use in understanding what happens to buildings is something called finite element modeling, something you learn through the course, which involves gigantic models of blocks of soil, buildings, interacting with each other, very complex. And these analyses might take days to run. They're very complex. And they can be very expensive. So in a recent London Underground project, they were costing about 100K, so very, very expensive. So one of my students developed simpler models. They're simple because instead of such a big model where you've got calculation nodes of 46,000 calculation nodes, we have here 154 calculation nodes. We can reduce the size and effectively reproduce the same sort of behavior. And it's much faster to run. This takes minutes to run. And it can save significant time and money. And it allows us, the model that she developed is on the top. The model that's more detailed is on the bottom. It allows us to see hotspots of where damage might start to occur. And it can reproduce patterns quite well, although it's much simpler and much quicker. So it's a practical outcome that can deliver something of value to building owners as well as the developers of this infrastructure. Now, the second point I mentioned is, simulations will go so far. We also need to monitor what's happening. What is happening in reality? And traditional monitoring is done with sensors. So I don't have a sensor here with me, but you would have, let's say, a sensor like this that's placed on a building. And what that would measure on its own is just the displacement of one point. That's what sensors do. They just measure where they are, which is not enough because you're dealing with large structures. Measuring one point tells you very little. So what we're interested in is this idea of using laser scanning. If you know about laser scanning, what it is basically, it's a laser meter. You can shoot a laser meter. It comes back to you within a fraction of a second, and you can find distances. You might have seen construction people who use that often. A scanner is that device which is placed on a motor, which turns around. So what it does, it turns around itself. It creates 3D geometries of the environment around it. It looks a little bit like that machine on the tripod. And you can get data like so if you look at this little detailed cornice on the top, that's what I have point cloud data of, the laser scan data of that. So each point represents, point on that object. And you can get, millions of points within minutes using this technology. What is the challenge with this technology? Well, the challenge is you can get millions of points, but how do points match onto each other? Because points are not really objects. A sensor is attached to a building. It's always measuring a specific place. But when you place a laser scanner, you place a different place every time. So we need to find ways to match point clouds. So here's a point cloud of a masonry wall, and here's another one. And the algorithm here, what it's doing is it's using geometric features of the surface, because the surface is quite rough, and the roughness is quite unique. It's using all these matches to determine the deformation profiles of these structures. And what that allows is that we scale up from having each individual sensor saying, one little piece of information to a system where you have continuous information, almost continuous information, which is really very powerful. And you can do quite a lot when that happens. So an example, you can find this crack from point clouds. Here we're using, so this is more traditional computer vision domain, but it's got very interesting applications in structural engineering, so I lovingly use it. So we can find clusters around cracks, we can separate them, we can find their separate motions, and we can map cracks, and we can find how big they are and how the deformations occur. And it's very accurate what we can do with this, which is really exciting. So, there's very exciting things that you can do when you apply these new techniques to find out something about your structures. So, and these sort of tools are going to be really important because, as I said, we're going to focus as structural engineers on reuse, on rehabilitation, on understanding better what we have and seeing how we can use it better. These tools are powering this sort of idea. Another example, earthquakes. This was from last year. There was a major earthquake in Turkey, which was a lot in the news in the UK as well. I'm Turkish, so I went to the disaster zone after the earthquake, and it was a really interesting experience. So some of this, by the way, some of this work was done by undergraduate students. I should highlight that because I had too much work at the time. I was going back and forth doing work on site. So this is a great thing about being at Oxford. So I had a student at college who wanted to do some work. So I gave him some analysis work. So he's done all of this. So what we were interested in here was, we have this collapsed building where you can see part of the building and the roof collapsed to the right. This is a 13th century church in the southeast, close to the Syrian border. And we wanted to understand what happened. So that's the idea of forensic examination. When you go there, you don't have any information. There is no construction. There is no drawing of the structure. So we wanted to find out what has happened. Why did this part collapse and the other ones didn't? And how can we quantify damage? So, what we're doing here is we're looking at that little wall where I have a arrow pointing towards, and the side view of that wall is like this. You can see how it's sloping out, and the colors here are showing how much that wall is coming out compared to the ground. That wall is leaning out by 30 centimeters. So that wall was on the brink of collapse, but it didn't. The one next to it collapsed, but that wall leaned out so heavily during the earthquake. So what the theory I had at the time, I'm not quite sure I believe in it anymore because we're doing some further analysis and it's getting always more complex. But the theory was that porch over there, that was a recent construction, a recent addition, prevented the wall to come out further and prevented the collapse, which is incidental, but it's fascinating. But it allowed us to get this laser scanning data, allowed us to get displacements, out of plane movements of this wall, which was really interesting, and it was the information that we didn't have at the time. So this sort of data becomes really interesting and useful to look at. Environmental hazards are another one that I wanted to briefly mention. So climate change is something that a lot of us are concerned with because it affects our assets. And every time there's a hot summer in the UK and the temperatures go above 30, we might start to have problems with shrinking and swelling of clays. And when that happens, you can get damage in buildings. And 30 years, 40, 50 years from now, they project that some areas of England, including Oxford, are going to get drier, hotter. So the question is, how can we predict behavior and ensure our building stock is resilient against this hazard? It's quite a complicated problem because we need to consider vegetation. We need to know a little bit about how trees behave, how tree roots behave. We need to know about soil and how water flows in the soil. And we need to know about building and all the interactions that there is. So one of my students is working on this. I've got 2 more slides only, so I'll breeze through these. Traditional structural engineering-wise, something that I'm really interested in is how can we strengthen our buildings. When you're dealing with historic masonry, you need to choose materials that are sympathetic. And something that's become really powerful recently is the idea of using surface mounting of reinforcements. So you can put stuff on the surface. It will just look like paint or plaster. And inside that, you can put reinforcements. And that reinforcement could be, in this case, basalt. It could be steel. It could be anything. We have a different idea. We use sprayable glass fiber. So little bits of glass, fibers of glass, inside a plaster. Okay, so because most of our walls are covered with plaster, we put just fiber in that. And what the fiber does is it protects, it gives it resistance against cracking. And you can see here the sort of the fibrous glass being sprayed on the wall, and you can see what it does. And you can see that before the strengthening, the building was like that. After strengthening, we almost get no damage. So, and it's just a little thin bit of plaster, so it can do amazing things. Again, just some more things that excite me. Sustainable structural systems, and this is something that new engineers will certainly have to work on. These are stone systems which are basically pushed against each other by using bits of steel, so in a way pre-stressed or pre-tensioned, so that you squeeze it, the stone remains in compression, although there are tensile forces on it. Because the stone is always remaining in compression, it remains strong. And you can have very long beams like this of stone, which is an idea that's now becoming very popular with architects. And we're looking at something called creep, which is a material property, which describes how a material will fail under constant loads. So there's a lot of interesting questions, because we're squeezing the material. It can still fail over 100 years, 200 years due to creep. And this is really not well known. For this technology to kick off, we need that sort of information. I know I've overrun. Just a very final slide, perhaps the most important one. Just reflections on the Engineering Oxford course. I think it's a great degree because it equips students for interdisciplinary challenges ahead. So you don't have to choose the engineering you want to do. You can do quite a lot of different ones. There are opportunities throughout the degree to participate in research, and you can do really practical applications if you want, or you can do more theoretical stuff. So the department has all sorts of academics who do different things. And course offering is getting more exciting. I said, masonry wasn't in the course, which is why I was interested. We'll now have it in this course at least. I don't know if that will make it more interesting or less interesting, but that's how it is. And courses will cover the basic materials needed to conduct work on all these sort of things that I've discussed. So I wanted to show you all this just to say that these things are not really far away at all from what you learn. And if you're so interested, you can actually participate in that sort of research when you come. And finally, just to say, Oxford is a very, very diverse place. So you will be welcome here if you decide to come. And you can find things that are of interest to you. The department is very big and offers many options for that. So thank you for listening. Sorry I've overrun.